Well, anyway, going back to this is pretty straightforward. This is a little bit more tricky because we've got to solve for T. And delta G naught at temperature T, we need to know the temperature T in order to plug the temperature into this equation to solve for delta G naught. We don't have that. And so what we have to do is we just do some substitution. We know that delta G naught is equal to delta H naught, minus T delta S naught. Temperature T, this is temperature T. So this is my delta G naught plus RT ln Q. And so now I need to know delta H naught at temperature T, delta S naught at temperature T. The reason I'm doing it this way is because we know we can make an assumption. What's the assumption we can make? What's the assumption that we can make here? See, we run into the same problem. We don't know what the temperature is, so we can't calculate these, but we can make an assumption. This is why I asked you, what is the assumption you have to make in this particular problem? Yes. If we do that, then this turns into a straightforward problem. That is, this is going to be delta H naught at 298 minus T delta S naught at 298 plus RT ln Q. So if that's the case, then we can get these values. And then what we'll do is we'll just set this equal to 0. When we set this equal to 0, then Q goes to K, because it's at equilibrium. When delta G, there's no driving force, so we must be at an equilibrium ratio rather than some initial ratio that we have. And then what we can do is we'll just subtract, maybe let's subtract a delta H or add this to both sides or do something to rearrange this. Probably what I'll do is I'll just add this and subtract that to both sides. So what I'll get is delta H naught at 298 is equal to T delta S at 298 plus RT ln K. And then just solve this for T. If I solve this for T, then we just get T, just factor out a T there. We just get a delta H naught at 298 divided by delta S at 298. If I factor out T, this should be minus. We're going to do that on both sides. Minus R ln of K. Like that. So now if I'm given a K value, I can figure out the temperature of that. And so given a K, to solve for T. This is what we were doing yesterday. Well, what we were doing yesterday is we had a target K value. We wanted this ratio, and then we want the reaction to stop at that ratio. Well, the only way we can get the reaction to stop at that ratio is make that the equilibrium ratio. Fortunately, K is a function of temperature, so we can use temperature to change the ratio, the product to reactant ratio. We expect different ratios at different temperatures. And so here, in yesterday's problem, we figure out what K value we want, we plug that in here. We've already calculated delta H and delta S. Just plug that in and then figure out at what temperature will I get that particular ratio and see if it's well, that's the temperature you'll calculate, but then you got to see, is it a feasible temperature? Is it something that you can actually achieve, experimentally or not? And just because we can calculate doesn't mean it's feasible. So sometimes we might calculate a temperature of minus 400 Kelvin, but is that, the calculation's correct, but is that temperature an achievable temperature? No, it's an impossible temperature. So in that case, we can't get that, the desired K value. All right, does that make sense? Whereas the problem in the test is not like this. The problem in the test is like we're solving for Q. Well, that's, we're just playing around with the exact same equations, just solving for a different variable. When we solve for, like in a problem like this, when we solve for something like K, let's do that here. Solving for K under standard conditions is easy. Solving for K under standard conditions This is e to the minus delta g naught over RT. But solving for k under non-standard conditions is a bit more involved. And so if we solve for k under non-standard conditions, what does that equation look like? You know, and so here we had, what did we have? We had the delta g under non-standard conditions is equal to delta g under standard conditions plus RT ln q, but we set this equal to 0, and then q goes to k. And so we can solve for k under k as a function of temperature. I'm still doing k in temperature here. But the problem is these guys here, temperature. And so we don't know, you know, if we're solving for the temperature, which is this T, the common mistake is people will use delta G naught at 298, which I mentioned yesterday. We don't want to do that. And so to avoid doing that, we'll just go ahead and substitute in here. Well, delta G naught is equal to delta H naught. We'll just say approximately. And since I already did that, I'm not going to rewrite that whole thing again. Delta H naught plus, what is it, minus T delta S, sorry, minus T delta S naught, 298. And so this helps us here. Now we have temperature as a variable here, plus RT ln K. And so we'll solve for ln K here. This is equal to 0. And so we'll get RT ln K is equal to, let's subtract delta H naught from both sides and then add this. So we'll get T delta S naught, 298, minus delta H naught at 298. And then what we're going to do is we're going to divide it by RT. And so we'll get ln K is equal to delta S naught over R, this is at 298, minus delta H naught over RT. And then I'm going to change this a little bit here. That is, I'm going to write this ln K is equal to minus delta H naught over R. Then I'm going to put 1 over T here, separate that, plus delta S naught over R. All right, so if I have the temperature, if I know the temperature, I can see, you know, how that's going to impact, or in other words, I can calculate my K, which would be the inverse log, the natural log of this. I can calculate my K at any temperature by knowing this. I'm not going to solve this for K. I mean, we just take the anti-natural log, but I'm going to leave it in this form. This is a common form for this. And so this shows me, you know, if I want to predict the K value at any particular temperature, I would need to know the temperature, delta H, and delta S. And again, these are going to be at 298, so this is not perfect. But it's pretty close. Now, there's some applications for this. You know, we'll look at one application of this. This is called the Van Hoff equation, I think. And that is, we'll take ln of K at temperature 2 minus ln of K at temperature 1. When I do that, I get, so I'm going to just take this. So I'll call this K2, this will be T2. K1, this will be T1. And so what I'll get is delta H naught at 298 over R, 1 over T1, 2, excuse me, plus delta S naught, 298 over R. Okay, that's my K, ln of K2 right here. And then I'm going to do minus ln of K1. So ln of K1 is going to be a minus delta H naught at 298 over R, 1 over T1, plus delta S naught at 298 over R. Okay. And then I'm going to use the property of logs. If I use the property of logs, then ln of K2 over minus ln of K1 is ln of K2 divided by K1. Yeah. And then that gives me this. So I'm going to simplify this here by factoring out the delta H naught at 298 over R 1 over T2 minus 1 over T1. Okay. And then the this part cancels, the delta S part cancels out of there. All right, so if I'm interested in individual K at some temperature, I could calculate that using delta H and delta S. If I know the K value, let's say I know the K value at 298, but I want to figure out the K value at any other temperature, I could use this equation here. This will tell me the K value at some other temperature, given one temperature. And then if I do one application here of this, so an example of using this equation is if I have A liquid goes to A gas. If I have A liquid goes to A gas, then K for this is just going to be, well, the activity of pure liquids is 1. The activity of gas is the partial pressure of the gas. And so this would be the partial pressure, or the vapor pressure of the liquid. We call this the vapor pressure. Vapor pressure of the liquid. That's what my K value is going to be. And so what I can do is I can substitute this here. You know, if K is just the vapor pressure, then I'll get ln of K, which would be the vapor pressure at temperature 2, over the vapor pressure at temperature 1. And so this is going to equal minus delta H at 298. This would be the delta H of vaporization over R 1 over T2 minus 1 over T1. Do you recognize this equation? This equation has a famous name to it. No, I'm sorry, I don't know if it's Van Hoff. That was probably kinetics, but this is very similar to what looks like the Van Hoff. It's not the Van Hoff. I forgot the name of it. But this one I haven't forgotten the name. This one is from chapter 12. Chapter 12. Starts with a C. Not Charles. Clausius-Clapeyron. This is the famous Clausius-Clapeyron equation. The Clausius-Clapeyron equation just comes from this. This is one application of this equation to generate the Clausius-Clapeyron equation from chapter 12. You know, there are different ways we can solve particular problems. That problem we were working on yesterday, I think the only thing we had left was the math. Is that right? Finish it. Well, I'll let you finish it. How about that? Okay, are there any other questions? From chapter 13 or whatever. You know, today in lab, we're going to be doing a recrystallization. So I'll talk about that, but we'll do filtration and recrystallization, so it's not going to take a terribly large amount of time. We'll give you 2 hours for that. So we have a little bit of extra time here. I'll use that time to Where did we leave off on that problem yesterday? Should we finish that one? Okay. So the problem yesterday was we wanted a specific K value, and we needed to know the temperature. And so there are two things. You could either derive the equation or you could just memorize it. You know, some people just memorize it. The temperature is equal to delta H naught. It's roughly equal to delta H naught at 298 divided by delta S at 298 minus R ln K. Is that right? This is a problem. The problem is when you memorize the equations, you go, is that right or is that wrong? You know, sometimes. So it's nicer to memorize fewer equations and then be able to derive the equations that you need from that. But some people have no problem memorizing the equation. This one is not particularly difficult to derive, you know, based on. So you could try that. And so the K value that we were after, what was the K value we were after? Yeah, okay. And then the delta H we had calculated, the delta S we had calculated, just plug it in. Did somebody calculate the temperature of this yet? You can try that. So I think it was pretty much done. So move on from that particular problem. Let's look at maybe, you know what? I know we have a test tomorrow, but or Thursday. Then we're all right. If we have a test Thursday, then we have time. Let's have a little quiz today. The quiz is going to be a low-key quiz. It's actually not a real quiz, say, because you could work. This is an open book, open notes. You could discuss this with your neighbors, your friends. On the test, it's not going to be open book nor open notes, and you can't discuss it with anybody. But let's do a chemical reactions. Let's call this chemical reactions. And so what we'll do here is we're going to take potassium dichromate plus some hydrochloric acid plus some ethanol. We'll just mix this together, and you know, I want you to predict the product. So predict the product means write the balanced chemical reaction for this. You can do it in net ionic form, predict products. Write the balanced net ionic equation. Then I want you to comment on the driving force for this. In other words, what do you think the driving force is going to be in terms of relative strength of driving force or relative driving force? Okay.